How do we actually describe complexity? We have three primary notations of complexity. We have big O, which provides an upper bound on my algorithm's number of operations function. We have big omega, which provides a lower bound on my algorithm. And we have big theta, which is both an upper bound and a lower bound. So it is both big O and big omega. What does this actually mean? Let's imagine the following plot. So I have some graph where the horizontal axis is input size, n, and the vertical axis is number of operations. And let's imagine I've written some algorithm that the number of operations as a function of n looks like this. So this is my function f of n, which is describing the number of operations of my algorithm. Big O means that there exists some function. So I say my algorithm, my function f of n, is big O of some function g of n if some constant times g of n is greater than or equal to f of n as n approaches infinity. This got kind of mathy, but what does this mean? It just means that some constant times my function g of n will strictly exceed f of n after some point. So let's imagine I have this function n. So this is just y equals n. So it's a linear function that for any given n, the y value is the exact same. We see that there's some time period that this function is actually under my f of n, but for big O, that doesn't matter. For big O, or let's say this is 2n, just so that we have a constant here. In big O, all big O cares about is that at some point, this point right here, my g of n times a constant, so g of n is just y equals n, times a constant, which is 2. My upper bound function is actually an upper bound from some point towards infinity. So after this point right here, f of n will never be larger than 2 times g of n. Therefore, I would say f of n is big O of n. This function n times a constant is strictly larger than f of n after some point. So let me actually write that down. So I would say f of n is big O of n. N times some constant is strictly larger than f of n after some point. Big omega works similarly. Let's say with big omega, let's say I have this function, some weird nifty function. Actually, no, I'll keep it as linear function starting at the origin. So let's say I have this function. Maybe this is 0.5 times n. So in this example, okay, so let's describe big omega. Big omega, we would say f of n is big omega of some function g of n. If there's some constant, in this case I'll say b because I already used a here, some constant b times g of n is less than or equal to f of n as n approaches infinity. So again, this got kind of mathy, but what does this mean? I have some function g of n. G of n is just n times some constant, 0.5 is some arbitrary constant, is strictly less than f of n as n approaches infinity. So unlike the previous example where g of n was actually lower than f of n for a little bit of time, in this example, g of n equals 0.5n, or g of n equals n, is always lower than f of n. So because as n approaches infinity, this constant times g of n is strictly lower than f of n, I would say f of n is big omega of n. Okay, so big O gave me an upper bound. F of n is big O of n because as n approaches infinity, f of n is less than some constant times n. And f of n is big omega of n because at some point towards infinity, f of n is larger than g of n times some constant. The last one is big theta. Big theta is just both big O and big omega. So we say f of n is big theta of g of n if, first the intuitive way, f of n is big O of g of n, and f of n is big omega of g of n. But mathematically, what does this mean? It means f of n is bounded on both sides. It's less than or equal to, or it's greater than or equal to, I'll use the same notation. Here I use b. b times g of n. Let me fix that up a little bit. And it's less than or equal to some other constant times the exact same function. So this g of n and this g of n, they're the exact same function g of n, but I could have two different constants, and some constant times g of n is always a lower bound on f of n, and some different constant times g of n is always some upper bound on f of n. So in this example, I already found those two constants. So if g of n is just n, so in all these examples, I was using g of n equals n in this diagram. I have some constant 2 that I could plug in for a, such that 2 times g of n, which is n, 2n is always bigger than f of n, and some other constant, 0.5, such that 0.5 times g of n, 0.5n, is always a lower bound. Same exact function, two different constants, now provides both an upper bound and a lower bound. This means that f of n is big theta of n. So I introduced all three of these notations, but it turns out that in reality, you'll almost always only care about big O. Big O provides an upper bound, and therefore it provides some notion of a worst case scenario. In the absolute worst case, I know that my time complexity will be less than whatever g of n is. It'll be upper bounded by g of n.